Assalamu alaikum. Today is our online lecture 18 and today is the last lecture for magnetism. So in today's lecture we will cover the remaining two topics, that is Maxwell equation and second one is electromagnetic spectrum. So let's start. Let's start with the Maxwell equation. As Maxwell is considered as one of the most important invention, not in the field of physics only, but also aerospace and all the mathematical, um, where we use mathematics, engineering, everywhere. So Maxwell equation, we can say, one of the most important inventions. It is one of the greatest achievement that was developing the concept of electromagnetism. The theory that electricity and magnetism are manifesting of same phenomena. So actually Maxwell gathered all the concepts and inventions, and by combining those like Faraday's law, Gauss's law, these, after combining them he gave a new theory or equations. There are four equations which give us clear idea about electromagnetism, about electricity and magnetism. So let's start. So there are total four you can say equations of Maxwell. So let's do one by one. So the first equation of Maxwell, and this equation is also known as the Gauss's theorem in electricity. I think I can write so that you will remain writing this. If I can write hidden arrows, pen, automatic. Okay, let's start with the Maxwell first equation. So the electric flux through a closed surface is proportional to the total charge enclosed by that surface. This equation states that the effective electric field through a surface enclosing a volume is equal to the total charge within the volume. So the first equation is actually related to the Gauss's theorem in electricity. So here we can add that this is the Gauss's theorem of electricity, so that you can understand. So what is the main idea behind this? The main idea behind this is, let's do with the equation. So the equation starts with with the closed integral, that is closed integral, and E represents the electric field because it is the Gauss's theorem of electricity. So here it's talking about electric field, and D that represents area of the surface, because this equation states that the effective electric field through a surface enclosing a volume is equal to the total charge within the volume. So E is electric field, dA is the area of the surface, that is equal to charge, you can say charge or enclosed charge, and permittivity of free space. So the main idea behind this equation is that wherever there is electric field, there will be charge, there will be enclosed charge there. So the Gauss's theorem of electricity said that we no need to ask if there is electricity, then we no need to ask that is there any charge or not, or if there is a charge, then we no need to ask if there is electricity or not, because they are both directly proportional to each other and they will be present there. If electricity is there, then charge is automatically there. So this is the Gauss's theorem of electricity, or you can say the Maxwell first equation. Now go to the Maxwell second equation. Maxwell second equation is, the first equation was related to electricity and this second equation is related to magnetism. So here we can write it, Gauss's law in magnetism. So the first equation represent about the electricity, second is it's a form of Gauss's law only with magnetic flux instead of electric flux. So everything is same instead of magnetic. So here what this equation represents, the equation first of all is the closed integral, B represents the magnetic field, this represents dA represents the area of the surface, and why it is 0, because this is north pole and this is south pole. I'm talking about magnet because the second equation is related to magnetic flux. And what was the magnetic flux? The lines were like this, I think you remember this. These are the magnetic flux from the north pole to the south pole, and these are in this shape. So they are always in a closed path, and we also read this in the property of a magnetic flux or magnetic lines or magnetic field, because they are closed line. So when they are closed, it will be equal to 0. So the second equation says that it's always a form of Gauss's law only with the magnetic flux instead of electric flux. So it's always in a closed pattern. That's why the second equation is magnetic field into area is equal to 0. Now talk about Maxwell third equation. Maxwell third equation is related to Faraday's law. Whenever there is a charge in magnetic field, we get electric field. Faraday's law tells us that a magnetic field that is changing in time will give rise to a circulating electric field. This means we have two ways of generating electric fields: from electric charge or flowing electric current, or from a magnetic field that is changing. So here this equation, that is Maxwell third equation, represents rate of change of magnetic flux. So this equation also says that whenever magnetic field is changed, Whenever there is a charge in the magnetic field, we get electric field. How? You remember in our previous lecture we studied that if there is a magnetic field and if we pass or put the conductor with the wire through the magnetic field, there will be electric charge in there because of the magnetic field. So that is the Maxwell third equation that clearly represent that there are two ways of generating electric current. First is electric charge and second is from the magnetic field, and you know how magnetic field create the current. Just when we pass through the magnetic field, because of the magnetic field effect, the particles start moving, and when they start moving they form electric current. So now Maxwell fourth equation, that is also known as Ampere's law. Ampere's law tells us that a following electric current give rise to a magnetic field that circles the wire. In addition to that, it also says that an electric field that is changing in time give rise to a magnetic field that encircles the electric field. This is the displacement current that Maxwell himself introduced. This means there are two ways of to generate a solenoid circulating H field. Following current, electric current or electric charge field, both give rise to the same phenomena, and this is the equation. If you are confused in this, then I tell you in simple words. In simple word, the Maxwell fourth equation says that change in electric field creates change in magnetic field. That is the main idea behind this, and I can also write it here so that you can remember. Change in electric field creates change in magnetic field. So these were the four equations of Maxwell. Let's do a quick revision. What is the first equation? The first equation says that whenever there is an electric field, there is a charge, and whenever there is a charge, electric field is present there. Second, what second equation said? Second equation said that in magnetism, or Gauss's law in magnetism, there is always a closed path. You know this closed path, magnetic field, so that is always equal to 0. What does the third equation say? Third equation says that whenever there is a change in magnetic field, we get electric field. What is the fourth equation? Fourth equation says that change in electric field creates change in magnetic field. So these are the four Maxwell equations, and where these equations are used. I think in our FSC we have read a lot of this. We no need to do the numericals and all these equations again and again. In this course you just need to understand what is the main purpose of these equations. So read these from the books and from these definitions, and in practical use I tell you, whenever there is a, you can say in aerospace, whenever we study space, we go in the space, we manufacture things, we do mathematical problems, we do construction, we do some type of designing, equipment designing. Everywhere these four equations or these laws are used. So these are most fundamental and important and very, you can say, greatest achievement in the field of physics. So now we go towards our last topic, that is electromagnetic spectrum, and this we will cover in our second part of the video.